Hello GATE aspirants, welcome to GATE Chemical Solution channel. This is 2-mark fluid mechanics question in the year 2021 GATE question paper. Please read the question very carefully and identify what is given and what you have to find out. So now we will see the concept for this problem, then we will go for the problem solution. If you are well aware of the concept, please skip the concept explanation part, then you can directly go for the problem solution. Okay. So the concept of this problem is the boundary layer formation in the straight tubes. From this we have to calculate the friction factor, okay, fanning friction factor. So we will see what is the boundary layer and how it is forming in the straight tubes. Let's say this is the thin wall straight tube. The fluid is entering with uniform velocity into the tube at the entrance of the tube. Whenever it is entering into the entrance of the tube, the boundary layer starts to form. This is the boundary layer. So as the fluid moves further, the boundary layer thickens. It means the thickness of the boundary layer is increasing. So from this side this is the thickness, from this side this is the thickness. So the center is the solid like flow or plug flow. It means the fluid from this point to this point will move with the same velocity, whereas the fluid in the boundary layer is varying. Here it is 0 and from 0 to it is gradually increasing from this point, and again the fluid is moving in the same velocity as the entering fluid velocity. Okay, if we move further, again the thickness of the boundary layer is increasing. Okay, so gradually the plug flow is disappearing. Here this is the length of the plug flow, right? Here it is decreasing, right? So it means as you move further, the plug flow is disappearing and the boundary layer is keep on continuously increasing. Okay, if we reaches at this one particular point, the velocity will be completely distributed throughout the tube and it is 0 at the wall and maximum at the center. Okay, this complete velocity distribution of the fluid is called as the fully developed flow. Okay, in the tubes this is defined as fully developed flow in the fluid. Okay, so we will see the definition of fully developed flow. So actually the boundary layer is defined as that part of a moving fluid in which the fluid motion is influenced by the presence of the solid boundary, right? Since because of the solid boundary, here the velocity of the fluid is varying, right? So at the center, the all fluid is moving with the same velocity as the entering fluid velocity. Because of the solid boundary, it is influenced by the presence of solid boundary. The motion of the fluid is influenced at this region. Okay, so what is fully developed flow? As the velocity distribution reaches its final form at one point of the tube and remains unchanged during the remaining length of the tube with an unchanging velocity distribution is called as a fully developed flow. Okay, if you reaches at this point of the tube, the velocity is at its final form, that is completely distributed from this end to center. Since it is symmetry at the axis, same velocity profile will be followed this side and this side, right? So this is the fully developed flow. So now we will see what is the transition length for laminar and turbulent flow. So the transition length is actually defined as the length of the entrance region of the tube necessary for the boundary layer to reach the center of the tube and fully developed flow to be established is called the transition length. Okay, so as per the definition, from this point to this point, this much length is required for boundary layer reach its center. So this it reaches the center from here to starting. This is the starting point and it keeps on increasing the thickness of the boundary layer and it reaches center here. Okay, at this point the whatever may be the length of the tube necessary to reach the boundary layer to its center of the tube, that is called as the transition length. Okay, it is varying for laminar flow and turbulent flow. How it varies we will see. For laminar flow, transition length required is calculated as x suffix t divided by d equal to 0.05 into nre. Okay, here x suffix t is the transition length, so that is the length required to attain fully developed flow in the tube. Okay, d is the diameter of the pipe. So already all of you know nre is the dv rho by mu. Okay, depending upon the nre value we can identify whether it is laminar flow or turbulent flow. Okay, for turbulent flow, this relation, suppose fluid entering the tube is turbulent and velocity in the tube is above the critical, the transition length is nearly independent of the nre and is about 40 to 50 pipe diameter. So the fluid is entering into the tube is turbulent and the velocity is above the critical velocity. In that case, the transition length is independent of the Reynolds number. Previously in the case of laminar flow, what it is, transition length depends on the nre, right? In this case it is independent of the nre. Actually this transition length is about to 40 to 50 times the pipe diameter. Okay, so for 50 mm of pipes, for example 50 mm of pipe diameter, it requires 2 to 3 meters of pipe length is necessary for the fully developed flow for 50 mm diameter. Okay, whereas in case of the fluid is entering the tube is laminar flow and becomes turbulent on the entering of the tube. Initially it is laminar and when moving into the tube it becomes turbulent. In such cases the pipe length required to attain the fully developed flow will be very long. Length is more, that is 100 times the pipe diameter most of the cases. Okay, to get the fully developed flow. Clear? Now we will see the solution for this problem. So density of water is given, pipe diameter is given and average velocity is given, and they have asked us to calculate what is the fanning friction factor for fully developed flow, and also they have given the pressure versus distance from the entrance of the pipe. They have given the relation, pressure relation with respect to length of the tube from entrance. Okay, so viscosity of water is not given, so all of you know viscosity is 1 cp of water for 1 cp. So by converting into CGS units to MKS units, we will get 10 to the power minus 3 kg per meter second. So we have to find out whether it is laminar flow or turbulent flow. Based on that we can identify at what point of the entrance tube we will get a fully developed flow, right? They have asked us to calculate fanning friction factor for fully developed flow only. So nr is dv rho by mu. So by substituting the corresponding values dv rho and mu, we will get nre value 50,000. It means the flow is turbulent flow, right? So since nre is 50,000, the fanning friction factor relation is given as pressure drop into diameter of the pipe divided by 2 into length, density and velocity square. This is applicable for all types of fluid flows. So in case of laminar flow, simply F is 16 by nre, right? But this for turbulent flow that is not the case. So this is applicable for all types of fluid flow, whether it is laminar or turbulent or transition region, whichever flow types. Okay, whatever may be the flow types. So I have explained, right? For turbulent flow, the transition length is independent of the Reynolds number. It is about 40 to 50 times the pipe diameter, right? So by taking like that, so in this region of 4 meters to 5 meters, pipe diameter is 10 centimeter, right? So 40 to 50 times the pipe diameter, you will get 44 meters to 5 meters. In this region you will get the fully developed flow. In this region, if you calculate the pressure drop delta P from the graph given in the problem, so by taking the pressure drop values, and delta L is 1 meter and GC is 1, diameter of the pipe is 0.1 in terms of meters, and 2, density of the water is 1000 and velocity is given in the problem, that is 0.2 2. So squaring it, we will get F equal to 0.0074. Clear? If you like the video, share and subscribe and give your valuable comment in the comment section. Thank you.